My talk is titled Hydrodynamics and Gravity, or perhaps Fluid Dynamics from Gravity. And in this talk, I'm going to tell you about a tight connection between relativistic generalizations of the Navier-Stokes equations and the equations for Einstein's gravity with a negative cosmological constant in certain situations. My talk is some of what I say will be reminiscent of the membrane paradigm of black hole physics, but it's different from it. Okay? The membrane paradigm, to the extent that I understand it, is somehow the statement that horizon dynamics, the dynamics of gravity in the presence of a horizon, is the dynamics of a fluid interacting. The statement I am going to demonstrate, I'm going to tell you about today, is of a certain context in which the low energy dynamics of gravity is fluid dynamics. Fluid dynamics interacting with nothing else. Okay? The identity of the two dynamical situations, namely Einstein's gravity in a long wavelength limit and under certain situations, and the Navier not interacting with anything, no other complications. Gravity in this context will be equal to fluid dynamics. Okay. While the connection I'm going to explain to you is in the end a connection between two classical equations, two sets of differential equations. The motivation for studying this connection is the correspondence of string theory. I'm going to start by telling you about the setup. That's disrupting things. The SCFT correspondence. Okay. It's long been argued that UN gauge theories reduce to effective classical systems in a particular large n limit. You see, a gauge theory based on n cross n matrices has a lot of degrees of freedom. Okay, and in any situation where an observable is averaging over many degrees of freedom, dividing by n, things become effectively classical because fluctuations are suppressed by the law of large numbers. Okay, essentially what those realize happens in quantum gauge theories based on the UN gauge group. The law of large numbers suppresses fluctuations in dealing with gauging. Okay, so this has been known for 40 years. An example of a UN gauge theory is this theory called n equals 4 Yang-Mills theory, a supersymmetric pattern of ordinary QCD. And where that n equals 4 Yang-Mills theory is on the UN gauge. Okay?
Shiraz, you need to change the mic. But sir, if you don't move so much.
Okay, so n equals 4 Yang-Mills theories are examples. These theories are confirmed. Define a line of fixed points, unlike QCD, in which the coupling constant flows to strong coupling no matter where you stop. Okay, the coupling constant here doesn't flow with energy. A line of fixed points labeled by the coupling constant of the theory, and the appropriate coupling constant in a large n gauge theory is a combination of the usual coupling constant squared times n, which is sometimes called lambda, or the 't Hooft coupling constant. Okay, so these n equals 4 Yang-Mills theories appear in a one parameter family labeled by lambda. When lambda is small, these theories are weakly coupled, well understood quantum field theories. They're more mysterious and interesting when lambda is large. In 1997, Maldacena identified the large n classical system that governs n equals 4 dynamics at large lambda. So I've told you that every large n theory is effectively classical. So we must have some one parameter set of classical systems for UN Yang-Mills theory labeled by a function of lambda. And what Maldacena did in 1997 in his celebrated ADS-CFT conjecture from this point of view is tell us what the large n system, the classical system governing n equals 4 dynamics is at large lambda. Okay, now actually Maldacena did a little more. In some formal way he told us what the classical system governing n equals 4 dynamics was at every value of lambda. But the answer was messy and only partly understood at arbitrary lambda. But at lambda there was nothing messy about the answer, and there was nothing ill understood about the answer. The classical system governed the classical behavior of n equals 4 Yang-Mills at large lambda. It was in fact a version of possibly the most Einstein's equations of general relativity, generalized to have a few other fields. Okay, it was 2b supergravity, supersymmetric completion of gravity, on a space-time that asymptotes to ADS 5 plus S5. Okay, so from this point of view, Maldaceno's ADS-CFT duality is identifying the classical system for large n equals 4 Yang-Mills theory, and realizing that it's not some mess as has always previously been supposed, but the most beautiful equation known to mankind. Okay, the gravitational description of field theory dynamics, this is a surprise, right? It's a surprise that field theory dynamics has anything to do with gravity. And one of the reasons it's a surprise we've not noticed it before, is that it applies only at very strong coupling. Only when lambda is very large, where we have very little intuition for what's going on with field theory. However, that feels like a bit of a cheat. You know, if gravity and field theory are really the same, it would be nice to sort of see that at work somehow. But if you want to see it at work, you want to know something about what quantum field theories do at very strong coupling. Now, so you can go back and ask, are there some generic expectations you have for quantum field theory behavior at arbitrary values of the coupling, even if you can't predict exact details? And there are some generic expectations. The one that I'm going to focus on today is that it's generically expected and beautifully borne out in, of course, hundreds of years of experiments, that any reasonable physical system, in particular quantum field theory, quickly equilibrates, thermally equilibrates when starting with a complicated enough state. You hit a system, it sloshes around, and then equilibrates. Okay? So, the first question you could ask is if this correspondence is correct. What is the gravitational dual of thermal equilibrium? This was answered just a few months after Maldaceno's original proposal in a paper by Witten, and his answer was that the gravitational dual to thermal equilibrium is what's called an ADS black brane. It's the ADS version of a black hole solution. It's a solution with an event horizon. This event horizon is translationally invariant, as you would expect for the equilibrium of a reasonable field theory, and it has a name. It's called the ADS black brane. Something that's sort of interesting about this answer is the following. We now have several examples of the ADS-CFT duality. Okay? Following feature. All of these examples have the following feature. In all of these examples, it turns out, for a reason that's easy to explain but that I will not, that there is a consistent truncation of the dynamics of all of these examples to Einstein's equations with a negative cosmological constant in the appropriate dimension. Okay? So for instance, the 2b supergravity on ADS 5 plus S5 that we talked about here admits a consistent truncation to Einstein's equations with a negative cosmological constant in 5 dimensions. Okay? And this is true for every known supergravity dual description of a conformal field theory across dimensions. Okay? And so what's consistent truncation? Consistent truncation means that if you've solved the equations of this simpler system, you can lift that solution to an exact solution of the full system. Okay? So somewhere in the dynamics of the big beast lies a simpler system, namely Einstein's equations with a negative cosmological constant. And Witten's description of thermal equilibrium, this black brane, lay within this universal consistent truncation sector. So somehow the description of thermal equilibrium, it seems, has a degree of universality about it. Okay? The properties of thermal equilibrium, at least some of them, those connected with the stress tensor, don't depend on what particular example of ADS-CFT we're looking at. They extend across many different examples. That's sort of nice. Okay, but, okay, yeah, I've given a few more details of what I said. This is Einstein's equations with a negative cosmological constant. The Einstein tensor, this is the negative cosmological constant. I've chosen units, okay, I should say, I'm working in little d plus 1 space-time bulk space-time dimensions, gravitational dimensions. And the duality will establish a duality between this system and a field theory in little d space-time dimensions, okay? So little d is 4 if we're talking about n equals 4 Yang-Mills. Okay, and the black brane solution that describes thermal equilibrium I've listed here. It's a metric with an event horizon that occurs at r is equal to 4 pi t by d. R is a radial coordinate that is not in the field theory, The remaining coordinates x mu and x nu, there are d of them, these are the field theory directions. The solution is translationally invariant, as you can see from the fact that there's no explicit dependence on the metric on x nu, and has an event horizon, as you can see from the fact that the coefficient of dt square goes to 0 at some particular value of r. This metric has two parameters, a scalar and a vector parameter. The scalar parameter is the temperature of the solution, the Hawking temperature of the solution, and the vector parameter is a 4 velocity, which is slightly fancy. You can look at this black brane at rest, in which case the 4 velocity is 1, 0, 0, 0. But then you can also take the solution and boost it to go to a solution with the black brane moving at arbitrary speed. Okay? So these are the equilibrium solutions I've talked about. Okay, now that's nice, but equilibrium is a bit boring. Okay? And you could ask, can one do more? Can one try to understand departures from thermal equilibrium in gravity and compare against field theory expectations? Okay? So ADS-CFT in principle allows us to study all dynamical questions of field theoretic dynamical questions in gravitational terms, so one could do more. So Einstein's equations allow us to study deviations from thermal equilibrium. Okay, so the first natural question to ask about this is at linearized order. We know what equilibrium's like. Let's linearize around this equilibrium and see what we get and compare with what field theory gives us. Okay, so what I'm going to now do is to describe to you the answer to the following question. Suppose you consider one of these black branes that represent thermal equilibrium, and you linearize Einstein's equations around them. Okay? And you try to solve for the spectrum of modes in this linearization, subject to two boundary conditions. The first boundary condition is that the mode far away at infinity reduces to ADS space. That's one of the rules of the ADS-CFT correspondence. The second boundary condition is that the mode is ingoing in the future event horizon. This gives you sort of like a particle in a box problem. Wave equation that you've solved with two boundary conditions. And as we're familiar with, in other cases with particles in a box, it gives you a bunch of quantized modes. Each of these modes gives you a dispersion relation. Okay, so in each of these modes you can have e to the power I kx arbitrary momentum, but then the frequency is determined in terms of the momentum by solving the eigenvalue equation for this particle in a box. Okay, so you generate an infinite set of dispersion relations. Omega is a function of k, labeled by some integers n. Now, you could ask, what happens to these omega as a function of k when k goes to 0? What is the massless limit? What is the low energy limit of these modes? Okay? Really, there are two possibilities. Either the answer becomes 1 over t, because that's the only scale in the problem from conformal invariance, or it becomes 0. And for almost all the modes, the answer becomes 1 over t. But there are 4 modes for which the answer is 0. Okay? So this problem has 4 low energy fluctuations, 4 low energy excitations. And you can understand this 4 very simply. These are simply the goldstone modes of the problem. The static solutions that we had were labeled by 4 parameters, namely a temperature and 3 velocities. So now if you take these temperature and velocities and vary them slowly, clearly time dependence will not be too rapid. Okay? So these are the goldstone modes of the black brane. Now, whenever in physics you have a situation in which you've got a few low energy modes and the rest are separated from a gap, that's sort of interesting. It suggests there's an autonomous system of equations that govern just the dynamics of these low energy modes. So Polycastro, Stanirats and so on focused attention on these low energy modes and worked out in detail their dispersion relations and asked if they could reproduce this by some field theory way of thinking. And they realized that the dispersion relations that we got were precisely the dispersion relations of linearized modes of fluid dynamics. Okay? Shear modes of fluid dynamics, provided an assumption. The viscosity to entropy ratio of the fluid was 1 over 4 pi. Okay, so great. Here we have our first hint that deviations from equilibrium in gravity are behaving in a very reasonable way, very field theoretic way. They're giving us the expectations we would have got from linearized fluid dynamics. Okay, that's great. But you might still consider that a bit boring, because it's equivalencing to linear systems. Gravity and fluid dynamics are both rich sets of equations because of nonlinear phenomena in these equations. Okay, question, is it true in any well-defined appropriate sense that the long wavelength but arbitrary large amplitude fluctuations about black brains map to nonlinear fluid dynamics? Answer yes, and this is what I'm going to tell you about in the next 5 or 10 minutes. Okay, this basically had to be true if this is what the ADS-CFT correspondence implies, because it's long been known that field theories in local equilibrium are governed by fluid dynamics, even if amplitude fluctuations are long, provided wavelengths are long. So this had better be true. ADS-CFT is correct. Can we see it? Okay. Fluid velocity fields, velocity and temperature fields, and then you open Landau-Lifshitz fluid dynamics and compare with the most general allowed form for stress tensor and current expansions as function of temperature and velocity fields. You find the answer does not lie in the class that Landau-Lifshitz said was allowed. But this is very puzzling because this is an exact calculation, it's an exact answer. So there must be something wrong with Landau-Lifshitz. And every work on charged fluid dynamics since. Okay, and the answer is yes. There's a certain situation in which that Landau-Lifshitz either weren't interested in or ignored. That is, if you've got a fluid that is allowed to violate parity, and there's some connection here with anomalies which I won't have the time to go through, there is a new term. There is a possibility, in fact a necessity for a new term in, let's say, the charge current of this fluid proportional to the vorticity of this fluid. This is a phenomenon that's completely new to fluid dynamics, and once you realize that it's true, can be argued generally from field theory, from general field theoretic considerations, as was brilliantly done by Sohn and Soroka. Okay? And once you've got this argument that it's generally true, it applies to all fluids, not just the fluids that come from ADS-CFT. It applies to the fluids in the center of, quark stars. Okay? So this is one example of a minor and indirect way in which string theory makes possible contributions to experimental physics. We get our physics right. Okay? Where people sometimes previously have got it wrong, in general ways, and that general ways applies to a large class of systems. Okay? Not just the slightly strange ones from the point of view of experimental physics that we study. Okay. Another generalization that I think Gary will talk about in his talk is the generalization to the study of superfluid hydrodynamics. There's a similar story here. Gary will review duals to superfluidity within the ADS-CFT correspondence. The basic theory of superfluid hydrodynamics was worked out again in beautiful papers by Landau and Tiza and Kalapnikov and followers in the 50s and 60s. They classified all terms that could appear in the stress tensor and charge current expansion of a superfluid. The most up-to-date result was given in a textbook by Putterman, which contains 13 dissipative coefficients. You do the calculation ADS-CFT, you find that they've missed one. There's one more. Then you can go back and correct the analysis because they just made a mistake. Okay, so ADS-CFT helps you to get your description of superfluidity correct. Okay, fine. Okay, this is my last part. As we described about the computations within gravity have revealed that standard equations of hydrodynamics are sometimes incomplete. Okay, these are equations that were written down like 60 years ago and have been accepted since, in some cases. Okay, it's clear from this observation that a complete and systematic theory of hydrodynamics is at present lacking, and I think there's a interesting general question in theoretical physics for how to produce the correct framework for hydrodynamics. We've so far been working on a case-by-case basis. Can you do better? I'm going to list 3 general principles that constrain the constitutive relations of hydrodynamics. The first principle is that the equations of hydrodynamics must always be consistent with the existence of a positive divergence entropy current. That is, you should never be able to use these equations to do a thought experiment that will allow you to make a perpetual motion machine. Okay? This constraint turns out to be surprisingly restrictive. You might think that it gives rise to inequalities in constitutive relations, but no, it doesn't. It cuts down the number of parameters that you could add if you were just working based on symmetries. And that this is true is basically pointed out by Landau in beautiful work 60 years ago. Okay, there are two other principles that one can use, and the principles go along. I don't have the time to review them, but basically, fluid dynamics can be used to compute long wavelength correlation functions of the stress tensor and charge currents in the field theory. And there are certain general constraints that these correlation functions must have. The condition that the correlation functions computed from fluid dynamics obeys these general constraints gives you certain constraints on constitutive relations in fluid dynamics. Okay, there's one more such constraint that I won't tell you about, and we may not have thought of all of them yet. Okay, now it would be, I think, really interesting to find the full set of constraints that constrain hydrodynamical equations and understand this well. And one of the reasons I think this is really interesting is the following. You see, I've told you that, well, if I'd gone less fast, I would have told you that the constitutive equations, the possible terms in the equations of fluid dynamics are constrained in a sharp way. The number of parameters you could write down is cut down by the requirement that the dynamics admits an entropy current compatible with the equations that is of positive divergence. Okay, now this thought, okay, so suppose you take the equations of perfect fluid dynamics. Turns out that these constraints are automatic then. You try to correct the equations of perfect fluid dynamics with one derivative corrections. Not all terms that you can write down allowed on symmetry grounds are allowed. Some of them would violate this requirement. This is what turns out. This thought suggests to me an analogous question in Einstein's theory of relativity. You see, we've got, think of Einstein's equations like the perfect fluid equations. Think of alpha prime corrections, higher derivative corrections to Einstein's equations like the corrections to fluid dynamics. Could it be that the requirement of entropy increase in higher derivative of gravity constrains possible additions to Einstein's equations? Sounds like an interesting thought, but it's more than an interesting, it's more than an more than an abstract and unstudyable thought, because there is a sense in which the fluid gravity correspondence, the correspondence between fluid dynamics, I'm out of time, just 1 second, fluid dynamics and gravity actually maps a question into fluid dynamics into the question I've asked you about. Okay, so I don't have the time to tell you about this, but this is something that you can use the question of whether it's true or not, whether possibly corrections to Einstein's equations are constrained by the low energy requirement that the second law of thermodynamics always hold. Okay? It's possibly an answerable question, at least in long wavelength expansion in ADS space, using the map to fluid dynamics. Okay, so I conclude. So the last thing I told you about is ongoing work. I don't know what the answer is, but I find it exciting. Okay, conclusions. Asymptotically ADS, gravity reduces in the long wavelength limit to the equations of d+1 dimensional Navier-Stokes, the relativistic generalizations of the Navier-Stokes equations, with gravitationally determined dissipative parameters. Okay, the full set of Navier-Stokes equations has an infinite number of coefficients. First derivative, second derivative, any seventh derivative, 100th derivative order. Okay, all of these are computed by Einstein's equations. This, if you were studying the field theory, you want to know about the fluid dynamics of this field theory, it would be incredibly hard to get this information any other way. Okay, the gravitationally determined fluid dynamical system has no free parameters, so enjoys a degree of universality. Values of these parameters are interesting and sometimes surprising. One of the surprises was, as many of you have heard, about the low value of the viscosity. This map between fluid dynamics and gravity allows us to reword open problems in fluid dynamics as problems in gravity. For instance, you could try to use this gravitational picture to study turbulence. Who knows if you can say something using locality in the bulk that is not manifest from Navier-Stokes equations. Okay? Because these are the same dynamical systems. Anything that happens in one happens in the other. Maybe it's more manifest in one than the other. Okay? And it would be very interesting to extend this connection past the large N limit that I've been discussing through my talk, or to gain new insights into the structure of corrections to Einstein's equations, as I alluded to before. Sorry for going over time. Thank you.
We have a couple of questions suddenly, but the chairman, I would like to...
Well, there have been a number of papers, but almost no results, if you get my meaning. And nothing interesting yet. Yes.
Where are the difficulties?
Well, the difficulties is that you're mapping a difficult problem to a difficult problem.
That's right.
And so this duality is true. The question is, in the context of turbulence, is it useful? Can you say something about turbulence from the Einsteinian point of view that was not manifest from the Navier-Stokes point of view? So the question is it useful? So far, in my opinion, nobody's managed to make it useful.
Supposing you say that the turbulence is information losing, can you do some correspondence then?
I don't know. Let me tell you what I think you might. The map between these two equations is rather direct. This, from the point of view of learning something, is a bit disappointing. When you reformulate equations in a crazy way, it's more likely you learn something from this reformulation. However, there's one thing in this map that I think is interesting possibly from the point of view of turbulence, and that is ADS space has one extra dimension. Now, in other contexts of the ADS-CFT correspondence, this extra dimension corresponds to scale. Things that are big happen low down in this dimension. Things that are small happen high up. Now, this suggests that in fluid dynamical phenomena, for instance, big vortices can be separated just by locality from small vortices. Okay? So it suggests a way of geometrizing scale separation, which my understanding is, and knowing nothing about turbulence, which anyway in my crude understanding is a quite central part of the way of thinking of turbulence, this locality and scale. I feel that this might be the one useful payoff for the study of turbulence.
Two related questions. Are you restricted by ADS-CFT, and what's the difference between your work and that of Padmanabhan?
Okay. Am I restricted by ADS-CFT? So the map that I demonstrated was a map between gravity in an asymptotically ADS space and fluid dynamics. This is completely classical statements, an equivalence between two differential equations that doesn't require any correspondence, just the identity of two dynamical systems, but was suggested by the ADS-CFT correspondence. Now, you could ask, can you extend this in a way where the gravitational system lives in something that's not ADS? And some such extensions have been performed. What's crucial from our point of view is that the space is one in which you can naturally put a boundary condition, a reasonable boundary condition. So for instance, the near horizon geometry to D2 branes or to D5 branes or something like that, that's easy and has been done. Okay, these are not ADS spaces, but they're spaces that are in some sense qualitatively like ADS space. Okay, that's not difficult, has been done. The kind of thing that I've done would be hard to do in flat space without putting a boundary condition somewhere in the middle of flat space. Now that's what Strominger has done. Okay, so Strominger's work, which is essentially following up our work to try to mimic it in the flat space context, is basically mimic the boundary condition on ADS by putting an artificial Dirichlet boundary condition at some point in flat space. There also you showed that equations of gravity with infalling boundary conditions at the horizon and Dirichlet boundary conditions at a cutoff surface are related to the equations of fluid dynamics, possibly making strong connections with the membrane paradigm. Okay, now what is my connection to what is the connection with what Padmanabhan does? In this context, I suppose the question could be reformulated as what is the connection? Well, at the technical level, it could be reformulated as the question of what is the connection between what we did and Damour's membrane paradigm. Okay, these are very different sounding statements to start with. Okay, let me list the differences. Firstly, Damour's membrane paradigm works on any null hypersurface. You never have to solve some equations of motion. It's basically a kinematical observation, right? You take Einstein's constraint equations on a null hypersurface, you can rewrite them in a form that starts looking like fluid dynamics. Okay? But there's no claim that this is the only dynamical degrees of freedom of the system. This fluid, wherever it is, interacts with all the modes in the bulk. Okay? In our context, there's a particular low energy limit in which Einstein's equations reduce to the equations of fluid dynamics. Okay? Every solution with the caveats that we will list of Einstein's equations is a solution of fluid dynamics and vice versa. So it's a very different kind of statement. To get this statement, we had to solve equations of motion. Okay? And we had to solve the equations between the horizon and infinity where there's another boundary condition. Okay, a related thing is that our fluid is not just non-relativistic Navier-Stokes equations with no parameters. It's an infinite expansion in derivatives with a lot of dynamical content in each of those coefficients. Okay, these dynamical parameters are helping people who are doing simulations at RIC and LHC. So, okay, it's quite different. Is there a deeper, is there a deeper philosophical, is there some deep underlying connection? Possibly. Padmanabhan wants to say that gravity is the thermodynamics of some underlying degrees of freedom. Okay? Well, we have one example in which gravity is emergent. Gravity emerges out of n equals 4 Young-Mills. In situations in which the n equals 4 Young-Mills is at finite temperature, gravity does appear to be the emergent dynamics of some underlying degrees of freedom, namely the quarks and the gluons and the quark-gluon plasma. So I think there's some connection here, but I don't know what more to say. Sorry for the length.
So the Einstein equation, in your theory, it has only one parameter, it is the d, the dimension.
Yes.
Now, of course, there are d into d plus 1 by 2 Einstein equations.
Yes.
So the integration constants will be d into d plus 1. So d into d plus 1 plus 1, that is the number of free parameters you have.
Free parameters in what? In solutions to equations?
I mean, the fluid dynamics, which you have the correspondence of the different kind of fluid dynamics, they can have only d into d plus 1 plus 1 number of free parameters.
The solutions to fluid dynamics? Or the equations of fluid dynamics?
Equations. No.
Oh, yes.
Kind of.
No, sorry? The solutions of the equations, I'm not understanding.
No. So, your Einstein equation,
Yes.
every solution will correspond to a different fluid dynamical
Solution, yes.
But the number of parameters of your Einstein equations,
Of the equations, not the solutions.
including the integration constants.
The integration constants are properties of the solutions.
Right.
So let's separate properties of the equations and the solutions. So equations are just uniquely determined.
Yes.
Solutions have D, right. So let's fix D, there are no parameters. Okay.
But
Now, the solutions have as many parameters as there is initial data for fluid configurations. Because I found a solution for every u mu of x and t of x that obeyed the fluid dynamical equations. Now the fluid dynamical equations, formulated as initial value problem, are labeled by u mu of x and t of x at a given time slice, the first order equations. Okay, so as many solutions as u mu of x and t of x at a given time slice.
Your covariant derivative
Yes.
of given not the partial.
Covariant derivative, but covariant on the boundary. So in the simplest case, the boundary metric is flat, so it becomes ordinary.
Any other question? Otherwise, let's thank the speaker.